So here's again another abstract vector space. The made-up vector space. And often you would find examples like this in linear algebra textbooks when it tries to introduce abstract spaces. Because you know, linear algebra kind of goes hand in hand with the PDEs. But some people take linear algebra first and then PDEs, some people go the other way. And if you haven't seen PDEs, you really don't see the good ones. So the real nice examples of linear algebra comes from PDEs, because solution spaces, they come from PDEs. So they try to use some baby examples which has nothing to do with PDEs, but I still want to show you that such a space does become a vector space. So for example, if you have two polynomials that belong in V, then what does that mean? These are degree 2 or less polynomials with the condition that P of 1 is 0 and Q of 1 is 0, right? The question is this closed under addition of these vectors and scalar multiplication, right? So let's first check. If you have Px plus Qx, is this still degree 2 or below? Yeah, right? If you have degree 2 or below polynomials, two of them, you add them. You can't have degree 3 suddenly. Okay? If you multiply them, then you would have higher degrees, but if you just simply add, you can't have higher degree than 2. So this is still degree 2 or below. And it also has the property that if you evaluate at x equals to 1, what do you get? That's P of 1 plus Q of 1, and they're both 0, because that's the condition, so it's 0, right? Another thing is, if you take Px and multiply by any constant c, that's again degree 2 or below polynomial, right? And again, if you evaluate at 1, it's c times P of 1, so it's again 0, right? So scalar multiplication is defined, vector addition is defined. And because these additions and scalar multiplications are the usual ones that we use in algebra, it has all the properties like associativity or distributive property, you name it. Everything that you check for the 8 conditions for being a vector space, it satisfies it. So this set indeed is a vector space. Okay? Is that okay? Yeah. I didn't really write down the full proof. It could be a homework problem, giving you an example and go through all the lists of the vector space, and then you have to show that every property is true. Okay? So that could be a homework problem. Okay, so given that, now we have to find the basis for V. Let's try that. So a generic element in V would look like ax squared plus bx plus c. You agree? That would be in V. Anything in this element, because it's a second order or less polynomial, it should look like that. Okay. Now, is there any additional condition about A and B and C? What condition should A and B and C satisfy?
X is equal to 1.
It has to be 0, and what does that translate to? No idea. I mean, just write it down. What does it say? What's P of 1?
0.
Well, it's 0, but if you plug in 1 here, what do you get? A plus B plus C is equal to 0, right? So you see that you can solve this for any one of them. And if we choose to solve for C, we could choose to solve for A or B, it doesn't matter. In fact, choosing different ones will give you different bases, but you have many different possible bases for a vector space. Okay? So if I say C is equal to negative A and negative B, and you plug this back in, we see that generically, an element in V will look like this. Ax squared plus bx, and then minus a minus b. C is now replaced by that, right? Okay, then I can factor an a out, group these two and factor an a out, and get x squared minus 1. And group these two and factor a b out and write x minus 1. So now I've just proved that any element in V should look like this. But now look, x squared minus 1 itself is in V. Do you agree? It's a second order or less. If you plug in 1, it's 0, right? How about this one? It's also in V. It's a first degree, so it's less than 2, right? Less or equal to 2. And if you plug in 1, it's 0. Okay? So what I just showed is that any element in V is a linear combination of these two vectors. Because this is indeed a linear combination, don't you think? Right? It's A times a vector plus B times a vector. That's a linear combination of two vectors. So I've just shown that V is in the span of x squared minus 1 and x minus 1. Moreover, these two are linearly independent. Right? One is not any constant multiple of the other. Right? It can't be, because you can't take any constant multiple of a first degree polynomial to make it as a second degree. Right? And any constant multiple of a second degree would still be second degree unless you you multiply by 0. But if you multiply by 0, that's again not a first order, so it can't be. Right? So we know that these two are linearly independent and it spans the entire space, so this must be a list of vectors that form a basis. Is that okay? Right. So that's the answer to, so answer to part A would be that x squared minus 1 and x minus 1, this list is a basis. Right? Okay, but then how would you represent this? So part B is saying the following. Part B is saying, what is this x squared plus 2x minus 3? What's the matrix representation under this A, where A is this, let's call this A. So let's think about that. Okay, so x squared plus 2x minus 3. First of all, if you plug in 1, you get 0, so this is indeed in V. And because we have a basis, we know that this should be a linear combination of these two vectors. Right? So we have this A times x squared minus 1 plus B times x minus 1. And the easiest thing is it's ax squared plus bx minus a minus b. So a must be 1 and b must be 2. And then if it's 1 and 2, it automatically satisfies the third one. Therefore, this would be 1, 2. Done. Okay. So that's an example where you can have an abstract vector space, choose a basis, and represent any vector as a column vector.